But he was here as a pre-doc for a year, working with Scott Kenyon. After that, he moved to the University of Cambridge in the UK, where he was a postdoc before being awarded a prestigious university research fellowship by the Royal Society. And after which he moved to Warwick, and where he's going to be appointed lecturer as soon as his fellowship runs out. So, Grant, stage is yours.
Cool, thank you, Luca. Okay, so a lot of the work that I do is on these things that we call debris disks. So these are analogues of the Kuiper belt and asteroid belt and other small body populations that we have in the solar system. So these are analogues of these things, but around other stars. And one of the things that, and so normally we take images of these things. There's a snippet of one there. We take images of these belts around other stars with instruments like ALMA. But something that's actually been going on for a long time, since the 80s, but is now, I think the body of evidence is enough that I think we can start doing things, that there are things that we can reasonably call exocomets around other stars. So I'm not talking about Oumuamua and Borisov, which you might also call exocomets if you wish. But when we have more of those, of course, those are going to be interesting in a similar but different way. And so I do this work with a whole pile of people. Luca is one of them, and David Wilner, among other people. And so what I'm going to do is sort of tell you a story about this stuff with some of my work is interspersed in amongst this. So I wanted to start with a picture of a comet in the solar system. And this is Comet McNaught, which was I think it was either 2006 or 2008. It was basically immediately before or after I came here for my pre-doc. And so this is the picture to show you that comets can be incredibly complex. And so the data that I'm going to be showing you are not going to be showing you things like this. We want to really be able to, obviously, but we want to be able to, I think for a start, we want to be able to think of these things around other stars in a more homogeneous way, treat them like they're all the same so that we can develop theories, but we'll also have to remind ourselves that they're not all the same. And so this is why I've shown this picture. Now, in the solar system, comets promise to tell us a lot about how we got to the state of our solar system as it is now. So this is one thing that I've picked out. So this is essentially a combining of the results from various instruments on board the Rosetta mission to this Comet 67P. And the main thing that they inferred from this is that this comet is made of an aggregate, a loose aggregate of millimeter-sized particles that came together in a fairly gentle way. And so the inference that this supports these ideas of things that we call streaming instabilities, a way that you can directly form things like this that we call a comet, but in general planetesimals, so the planetary building blocks. And so this is a relatively recent, or an idea that is gaining a lot of traction now for how you form planetesimals. And so in the solar system, we have some kind of ground truth that appears to support that. Now, comets have to come from somewhere, right? They don't survive forever, and so there has to be a source region. And so in the solar system, we have the asteroid belt. So these are two graphics from here, right, from the Minor Planet Center. The left one shows the asteroid belt with Earth and Jupiter, and you can probably see in the faint blue here Trojans as well. And then on the other side, we have the Edgeworth Kuiper belt with Jupiter, Neptune, and Pluto, and all of these Kuiper belt objects. And so this is really one of the main source regions for our comets. These things get scattered down by the planets and appear to us as comets. And I guess I should point out that this looks like a very uniform distribution because we have good sensitivity to those objects. But over here we don't, and this is why it looks clumpy. There is clumpy structure in here, and that Pluto is in a 2 to 3 resonance with Neptune. But this would look much like that, given the sensitivity. So this is on the leftover list of questions that we would want to ask about comets around other stars. And so we would start out with asking, is there evidence for them? Do the data support that? And then beyond that, we want to then, given enough of these things, we want to say, well, what do they correlate? What sort of planetary systems do they reside in, given that we expect that you need to have planets to bring them close to other stars? What are they made of? And then, eventually, of course, do they deliver water? Is it a bad thing? Are they delivering impacts that are going to be bad for dinosaurs and such like? So, we can't really do these. We can do a little bit of this maybe, but really it's speculative. So this talk is about the first step. So what is the evidence for these things? And so in the outline is I'm going to talk a little bit about these debris disks around other stars and talk about some of the discoveries that have been made and then sort of try and give you a kind of an overview picture of them at the end. So this is the sort of picture that I have in my head of other planetary systems. So we can't necessarily detect all of these components, right? So we have some planets of various sizes at various distances. This is purposefully scale-free. And then maybe we have planetesimal belts or an asteroid belt that's closer to the star, and material can be scattered from there in towards the star. Or maybe it can be scattered in a way that ends us up with things like Jupiter family comets from further out. Or maybe they can be scattered out into an Oort cloud and then eventually come back later as long period comets. And so this is the sort of picture that I have. So if you're seeing comets, it'd be very hard to do that without having planets to generate them in the first place. And so what do we know about these source regions, the debris disks? Or for a start, what are they? And so this is my definition. It's a parent planetesimal population in a gas poor environment. And this is sort of, I've tried to craft this in a way that excludes things like protoplanetary disks or stellar winds. And normally what we think is happening is that there is a parent population which is colliding, creating dust, and then those fragments collide and so on down into dust. And the dust has a relatively short lifetime. And so we see the dust, but we infer that the planetesimals are there. And this was realised in the 90s, so not long after the first debris disks were discovered. And so to just give you a couple of pretty pictures. So on the left is an A-type star. So this is an ALMA image of the disk around the star. You don't see the star in the centre, HR 4796. And this is something that is sort of typical of a debris disk. So they're not all this narrow, but this is kind of what they look like. Whereas maybe you've seen this ALMA image of HL Tau. So this is a protoplanetary disk in which the planets are or have formed. And so this is an image of the dust, but there's a lot of gas there as well. So this is not the sort of thing that we're talking about. Although you could have a debris disk hidden inside there that we haven't seen. And then there are other things that are not debris disks that we also image around other stars. And then, of course, as soon as you try and start putting things into boxes, you realise your boxes are inadequate. And so we have things like HD 141569, which some people want to call it a debris disk, some people want to call it a protoplanetary disk, and it depends a bit on which part of it you look at. But it has rather more CO than we really think should be there for a debris disk. So there are always going to be things that defy your classifications. And just to show you a few more pretty pictures. So these things have a variety of structures, but typically, they look like rings of varying width. Sometimes they have substructure. So maybe there's just naturally a gap, a depression in the dust there. Maybe there's a planet that's clearing it out. And so these are the sort of images. Most of these are with ALMA, but we also take images. For example, the two at the left are images in scattered light. So we image these in various ways. And the typical scales of these things are of order 50, 100 AU, so not so dissimilar to the solar system. Okay, so we call comets, the definition, we define comets by these things that are close to the sun with tails, but of course we can also more broadly just call those planetesimals that happen to be losing material because they're close to the star. So if we put these things back into their source regions, then they're no less icy when they're out there. And so I want to show you a couple of things that there's mostly work done by Luca that we're pushing towards trying to get at the composition of these bodies in situ before they're scattered down to be detected as comets. And this turns out to be hard. You don't just take an image with ALMA and get a nice image of the CO like you do for protoplanetary disks. And so the trick that Luca has developed is basically to look at where the dust is. So this is a very nearby system, 7.7 parsecs, called Fomalhaut, which has a bright and narrow dust ring. And so then what you can do is you can figure out what the geometry of this ring is. If you know the mass of the star, you know what the velocity of the material should be at any point in this ring, but you don't know if the disk is inclined like that or like that. But you can try those two cases out and basically co-add all of the little bits of your cube and make a spectrum. So if you don't bother if you just look in your cube where the dust is, you get the top plot, and you maybe get a hint of a detection at the CO line. But then you try these two different possibilities for the orientation of the disk, and in one case you get nothing, and in the other case you get something, and so you've detected CO. And the interpretation is that this CO is being released at some point in the lifetime of a planetesimal, from when it's a large 10K object, say, to when it gets down to a micron-sized dust grain and gets blown out by radiation pressure. So I can't tell you when that CO comes out definitively, but it must come out at some point because we see it. And the other inference, so we don't think that this CO is just a remnant from a younger phase, a younger protoplanetary disk phase, because the lifetime of the CO is very short, about 100 years. So you really need to keep replenishing it. And so the next thing that you can do is, with a few assumptions about the rate at which you're processing stuff through your collisional cascade, so the mass loss rate in solids, and then a lifetime of the CO, then you can, and the amount of mass in CO that you observe, then you can make this plot. And so this is the first attempt at trying to figure out how much of the mass in a planetesimal in the planetesimals on average around the star Fomalhaut are made up of CO and CO2 as compared to a few solar system comets. And so the error bars are large, but we've only just started this. But so far, at least, it looks like the compositions, at least for CO, are fairly similar. So this is the sort of thing that we want to be able to do more of around other stars, is ask, are the compositions of these planetesimals similar or different to the solar system? Now, another thing is to go, okay, well, how should this amount of CO or other volatile material in the planetesimals change depending on, for example, how big the debris disk, the planetesimal belt that you see around the other star is? And so then, this is a plot that Luca made based on ALMA data, and what it's showing you is the radius of the disk, of the image disks, as a function of the stellar luminosity. And there are a bunch of biases that go into this plot, so that its interpretation is not totally straightforward. But at least here, what there is there's a significant positive correlation, and also on this plot are a few snow lines that have been inferred for protoplanetary disks. So the distance at which you get cold enough to freeze out CO, and so you might expect to have CO in your planetesimals. And these are roughly consistent, at least, with the slope of this trend. And then here is the solar system as well. And so the possible inference from this is that there is a preferred formation for the debris disks that we're seeing around other stars, which happens to enrich them in CO. Now there's one moderately unusual case, HR 4796. This is an A0 star, so maybe we're destroying the CO faster than for other systems. But this is one in which you would expect to see CO, and if not CO, then maybe carbon, which comes from the photodissociation of the CO, and that's not detected. And this is a bit smaller than average, so this is suggestive. Maybe this is smaller, so it's a bit too close to the star to put the volatiles in the planetesimals when they are forming. Okay, so to say something about the transits of these objects. So quite a lot of this is going to be about the star Beta Pictoris. And so this was really the first, unless you work on white dwarfs, this is the first evidence of planetary system material around another star. I'm not going to try and compete with Van Maanen's star. But so IRAS was launched, and the first thing you do with IRAS is you want to calibrate it. So you point it at Vega, and you realize it's got a huge infrared excess, and go, uh-oh, what's going on? But then a coronagraphic image was taken of another one of these infrared excess stars, Beta Pic, and this was the image that came out. And so this was interpreted as an edge-on disk of material around another star. And so something that looks like, an analog of our solar system around an earlier type star. And then the system has also been seen to have a directly imaged planet. This is a bunch of images showing the motion of this planet. So it is going around the star on a reasonably circular orbit. There is now another discovery of a second planet, and both of these are about 10 Jupiter masses at about 3 AU and 10 AU kind of orbits. So this is a very young system. So this is sort of for people who work on debris disks and planets, is sort of an all singing, all dancing system. If there's anything interesting that young planetary systems do, this one has it. And one of those things is these spectroscopic exocomet transits, and these were first discovered in the 80s. And so what you're looking at here is a spectrum of one of the calcium H or K lines. So this is an A-type star which is rapidly rotating. So you have this broad absorption just from the rotation of the star. And you have an absorption feature here which is interpreted to be from a stable circumstellar gas disk that is going around the star. This is why it's at zero velocity. And this is always there. And then you have these other things which are sometimes, well, there's always something in the spectrum, but they're at different velocities. And these things were at the time called FEBs, falling evaporating bodies, because if you said exocomets, you didn't get your paper published. So this is something that has taken a while. And so this has been almost not exclusively, but a lot of this work is done by French groups in Grenoble and Paris, and so they've really worked hard to make this a thing, and have developed models, which I'll show a little bit more in a minute. And so then this is a more modern spectrum taken with the HARP spectrograph. So lots and lots of HARP spectra of the star have been taken, which is great because HARPS is made for detecting planets, and so it's for this kind of work, it's essentially perfect because it's stable, and we don't need meter per second precision. And so what you're looking at is just a nicer version of the same thing. There's a circumstellar feature and a bunch of other features which will be different every night, which is what you would expect because it would take a few hours for one of these objects to go across the face of the star. And so from this, you can say that this has been ongoing at similar levels, for several decades. So you can't say that we're not looking at a special time, but at least we're not looking at a special 1 year period in the lifetime of the star. Now, one of the things that was also done by Flavien Kiefer with a bunch of these French guys was essentially to take about 15 years of these spectra and then essentially fit Gaussians, upside down Gaussians, to all of these features and look at their distribution. And if you take the distribution of the radial velocities, you get this plot over here. And so the way that they interpreted this is that there are two populations. There's this broad population over a wide range of velocities, and then there's these things that are at relatively low velocities, which would mostly likely imply that they're further away from the star. And so if you plot this in a different way, and this will probably come out as a bit surprising to you. So this is surface ratio, which is literally the fraction of the star covered by this coma. So we're not talking about the nucleus of the comet, right? Because if we could see transits of comet nuclei, then that would be surprising. Against the depth of the absorption. And so this is essentially the same populations, these blue and red populations, and their interpretation is essentially that you have these young comets which are relatively far from the star, and they're very efficient at taking the stellar flux and converting it into a very gaseous coma, whereas these ones here are more depleted and do not cover as much of the star. They're not outgassing as efficiently for a given amount of stellar input. And so I don't think they say this in their paper, but I was in France earlier this year, and Flavien Kiefer, when I put this plot up, he said afterwards that this reminded him of this radius gap that you see for exoplanets. So there's this radius gap where it looks like photoevaporation is taking planets that have relatively large atmospheres and photoevaporating them across this gap to have much more stripped atmospheres. And so maybe this is a similar kind of process, and that these ones are young and their orbits evolve and they end up down here. There's no model of that, it's just a qualitative picture. And so another thing that we have is physical models that, again, the French people have developed for these comets, and these are, they're complex enough to reproduce what we see, which is the important bit. And the main thing, so what you're looking at here is a bunch of the calcium as it's distributed around the nucleus in this kind of bow shock shaped coma, and the absorption that you would expect, and a plot of where it is relative to the star. And so in this case, one case it's 20 stellar radii, so we are talking about being very close to the star, and in this case 10 stellar radii. And one of the important predictions that this makes, and which they've actually used to make inferences, is that the closer the comet is to the star, the more heavily the coma is ablated by radiation pressure, and so the smaller it is. And so what these guys actually do is that they take this model and use that to infer the distance. Now, one thing that I realized when I was looking at these spectra, so there are now like 5,000 HARP spectra of Beapic. It's totally insane. But it's been observed a lot over the last 15 years. And so what you do, so some nights there were just a whole series of spectra taken, one after another, for several hours. And so what you can do is actually, if you plot a whole lot of them stacked up like this, then you can see that some of these features move. And so maybe you can probably see that there's a diagonal stripe in the top plot, and if you can't see that, then in this plot of stacked spectra, you can see that this event moves. And this is not, in hindsight, that's not all that surprising. We're saying that these things are at a few tens of stellar radii. Of course, they're orbiting, so they're accelerating. And so we should be able to detect acceleration. It turns out that that's true. And so I had a look through most of the spectra where there were an hour or so of observations on any given night. And then you can see a bunch of these accelerations where you just have these diagonal features with little dotted lines to guide the eye. And so what this does is that it gives you a measurement of the distance of the object to the star. And so what I did is I basically did this Markov chain Monte Carlo fitting thing where I could get posterior distributions of where the objects are relative to the star, and that's what these clouds of dots are. Basically the distance from the star at transit and the velocity that it was going at. And these transparent dots are ones where the acceleration was not constrained, so you don't actually know where it is. You just have a lower limit. And what it turns out to show, so these boxes show where some of these features were inferred to be from the physical model, and my inference from the accelerations is essentially the same thing. I see that the velocity of these things is a bit high for a given distance, but I'm not as sensitive the way that I did this to low velocity features, because as you can see, there's very strong absorption from the circumstellar line at low velocity, so it makes it much harder to disentangle the accelerations. But this was more of a proof of concept than a really hardcore attempt. So I think there's more to do. And the other thing that you can do from this is just look at the absorption, which is the y-axis, versus the distance to the star. And in cases where the acceleration is detected, you do see what you expect, which is the depth gets deeper as the objects get further away from the star, so that the comae are getting bigger. Okay, so that's the spectroscopic transits, and what I haven't gone into, that people are trying to detect these around other stars, and there is one, for me, there's one convincing case, and there's a bunch of not so convincing cases, and I think there are a lot of HARP spectra, right, because everyone's been using it to look for planets. But I think there's more work to be done to try and extract these from spectra. So that's a watch this space. Okay, so photometric transit. So you find these things in spectroscopy. Corot is coming, the European Transiting Planet Mission, and so Alain Le Cavalier said, all right, well, what should we be able to detect with a very good photometer. And so he made some models to figure that out for different comet orbits. And so this is one example where you basically have a transverse transit across the star, or one where it's actually on more of a radial orbit, and you get these different shapes. So this, given low signal noise, looks pretty much like a planet, or an eclipsing binary, whereas this is a bit more characteristic. And so this was in 1999, and then nothing really happened. Now, the first thing that was interpreted as comets around another star was this the star named Tabby's star, KOC 8462857, which has this weird light curve over 4 years, which has a relatively deep dip somewhere halfway through the mission, and a bunch of dips just as the second reaction wheel failed. And so in the original paper, and another paper that Mark White led, we interpreted this as a family of comets. So the picture is that you've had some large object that has come in close to pericenter sometime in the past and is broken up and is spread out, string of pearls, much like Shoemaker Levy, and it's been sufficiently spread around the orbit that essentially your model has so much flexibility that you can fit anything. And so, but it has some nice properties in that you don't need to have a huge amount of dust because it can be spread along a relatively thin torus. And so there are some good things about this model, and it has some other things that I won't go into. But this is a very unusual star, so it's not to say that that's the answer. So then the next thing that came was that Saul Rappaport and some of these amateurs that he worked with looked through by eye a huge number of, all of the Kepler light curves, and they've been finding all sorts of weird things, but this was one of the things that they found, which was something that looks eerily like the predictions from 1999. And so the interpretation is that this is a comet going in front of another star. The depths of these things, they discovered several, are about 0.1%. And you have the steep ingress, a shallow egress, which is reminiscent of a transverse transit of a comet with a tail. And I found this, I think I found this insane. Maybe I'm lazy, but I didn't. I'm like, really, you look through all of these light curves to find something that looked like exactly what it should have looked like. And so I went across the hall to Simon Hodgkin, who works on transiting planets. I was like, this is insane. We should just automate this. And so we got a very good fourth-year student to make a more automated method to try and clean up the light curves a little bit, and then do some kind of asymmetry metric to look for asymmetric transits, much like the one that Saul published. And so this is just showing the method in this paper. It's pretty simple. Basically, we take a light curve, which is this light curve at the top, which has some periodic noise, presumably due to stellar rotation, and then we basically subtract, you use Fourier transforms to subtract sinusoids until you've made the light curve flatter, and then you run a box across it and see if you find something of a certain width that has a high signal to noise. And then we do that for all of the Kepler data. And then what we do, given these transits, then we want to try and quantify the asymmetry in some way, because obviously there are going to be lots of symmetric transits in these data. And so the way was pretty simple. You basically fit a symmetric transit, which in this case was a Gaussian, and then you fit an asymmetric transit, which is a Gaussian on one side and exponential on the other. And then just divide the chi-squared from those two to create this asymmetry metric. And then we can make this plot. So it's a signal to noise, so how deep, how high is the signal to noise of your transit versus how asymmetric is it. And then, and over this way is more symmetric. And then we can take a look at the objects that fall in this particular box, which is basically informed by the ones that were in Saul's paper, to see how many they missed. And we found a couple that looked plausible. Of course, if you're looking through light curves for 200,000 stars for 4 years, you're going to find, it's surprising we didn't find more rubbish, to be honest, but we needed to take a look through these, and there are some artifacts, but we recovered the ones that they found, and we got some new ones. Now, the thing that really worried me about this is like, okay, so you look through a huge number of light curves, which have all sorts of systematics, believe what you've found? And the thing that eventually convinced me was to make and that I guess is made possible by Gaia, is to make an HR diagram that includes the objects that we concluded had comet-like transits and a bunch of stars that have similar parallaxes and similar parts of the sky in the Kepler field, and you end up with this plot. And so, Kepler was looking for planets around Sun-like stars, so most of the objects are here, and the objects that we find these transits around are A and F type stars. So this gives me confidence that we're talking about something astrophysical here that is related to the stars in question, because it's improbable that systematics would appear for these stars. Now the thing that I think that it really nails it for me. So now we have TESS. So the problem with Kepler is it looks at this patch of sky which is chosen to have lots of stars in it, but doesn't have many young stars in it. And I would expect, interesting things happen in roughly log space intervals in a planetary system. So we want to look at young stars for these objects. And so Beta Pic was observed by TESS in 6 sectors, so 6 lots of 30 days. And you get a light curve that looks like this. And if you sort of squint, you can see that there's a bit of a depression in the light curve here. But we can do a lot better, because it turns out that the Beta Pic is a delta Scuti pulsator, so all of that scatter in the previous plot is not noise. It's about 50 cycles per day of pulsations from the star, which you can then relatively easily subtract off. And then you get a light curve where we've done some cutouts here to show three comet, well certainly 1, possibly 3 comet-like transits for Beta Pic. And so, given that we know that there's a huge level of cometary activity from all of the HARP spectra, and that gives us confidence that if we look at this star, we should expect to see something that looks like a comet-like transit. And of course, this looks like the predictions as well for a transverse transit. But then I find this confusing, right? Because we've seen all of these spectroscopic transits, and we see them because of their radial velocity. So they're not going transverse across the face of the star. They're on orbits that are consistent with being eccentricity of 1, so parabolic. So it would be surprising to see something that looked like it was just going in a transverse way across the star. Now the other thing that's weird is that if you fit so it's hard to figure out what the velocity of this object across the face of the star is, because it could be something that's very compact that went across relatively slowly, or it could be something very big that went across very fast. So there's a degeneracy that you can't really break. But what you can do is you can come up with a minimum velocity by assuming it does have a hard front edge. And so that's what the red line in this plot is a fit of a simple curtain model, which is basically a hard front edge and an exponential tail. And what you infer from that is 20 k's a second, so something that's at a few AU from the star, not 20 stellar radii. So it could be going faster, and it almost certainly is. Like it's relatively very unlikely that the eccentricity would be very small, because you wouldn't expect something to survive going around in a circle around an A-type star at 3 AU for very long. And of course, the transit probability just goes down as you go further and further away from the star. So you would expect the first thing that you would detect is more likely to be as close as it possibly could be. So probably closer. And so we haven't developed models of this, but the picture that I'm trying to put together is based on, essentially based on this plot. So it's surprising that we didn't see more transits with TESS for Beta Pic, right? Because from the HARP spectra, we know that there's essentially multiple of these things in front of the star at any given time. So it's really astonishing that we didn't, or naively astonishing that we didn't see multiple things going in front of the star that made the light curve a total mess. But presumably this is something to do with sublimation, and the picture that I have is sort of tried to be encompassed in this plot, and that we have comets whose pericenters are either coming down in one step to when they transit, or they're evolving under perturbations from a planet. And as when they're at a relatively large distance, then you can detect the dust. So there's energy that's going in, and it's sublimating water, and there is a coma, and you can detect this dust in these transits. But then when you get sufficiently close, then you can sublimate this dust, and this is presumably the origin of the calcium that I talked about. There are also UV spectra that see magnesium and aluminium even closer to the star. And so I think we can build a picture where this really is, we can treat these as the same comet. It's just they have different manifestation at different distances from the star. But of course, this needs to be put into a model. Since we've only really recently got the photometric transits, now I think we have enough evidence that these things exist and that they are something like what we think they are, and so we can build some physical models that try and make a consistent picture of this. Okay, so this is a slightly different tack on the same thing. So in the solar system, we have our exozodiacal cloud, so all of this dust that is near the Earth, out towards the asteroid belt and in towards the Sun. And some of this comes from the asteroid belt. We know that there are collisions in the asteroid belt, and some of them are recent because we see these asteroidal dust bands in the ecliptic. And pointing Robertson drag will bring that stuff down to Earth and contribute at some level to the zodiacal cloud. Now, also, we have Jupiter family comets, which are coming from the Kuiper belt, being scattered down eventually by Jupiter and sublimating, being destroyed and leaving dust behind in the inner solar system. And it turns out that essentially based on the scale height that is measured for the zodiacal cloud, the Jupiter family comets are inferred to be the main contributor to the zodiacal dust complex. And so this is saying that in the solar system, we think comets deliver the bulk of the dust that is near Earth. Now, so the question is does this have anything to tell us about other stars? So what we can do, and we do see warm dust around other stars at a variety of levels. Now, this plot is showing something. Is trying to show you what we would expect for warm dust around other stars. And so what this is showing is a quantity that we call the fractional luminosity. So it's the integrated infrared luminosity of the dust that is there divided by the luminosity of the star is there. So it's essentially the fraction of starlight captured by the dust. And then this is the evolution for belts at several different distances over time. And the important bit, and this is the same for planet formation or probably anything, right, that you're essentially controlled by the orbital time scale. So everything happens faster close to the star. And so for the collisional evolution, what this is showing, you imagine that you put down an asteroid belt or a Kuiper belt at different distances from the star, 1, 3, 10, 30 AU, and see how rapidly they decay. And the takeaway from this is that if you're at 1 AU, then you decay very rapidly because the orbital time scale is very short. And so this means that we shouldn't be seeing very large levels of dust in the habitable zones of other stars if it originates in situ in a debris disk-like scenario. Okay, so actually what I'll do is I'll go back to to talk about and measure habitable zone dust around other stars. So we can do this with infrared excesses to some level with an instrument like WISE or Spitzer. But that's okay for relatively extreme excesses, but it's not good enough to get anywhere near solar system levels. Now, people like me are interested in habitable zone dust because I'm a debris disk nerd, but people like NASA are interested in habitable zone dust because if there is a lot of it around another star that you want to point your HabEx or LUVOIR at to take a picture of an Earth-like planet, then you'll get photon noise from the dust that is there. And that could be a very bad thing if there is more of it than we expect. And so NASA funded this ground-based instrument called the Large Binocular Telescope Interferometer to go out and measure habitable zone dust levels around a bunch of nearby stars to try and assess this. Because this is the sensitivity of previous instruments that kick interferometer nulla were not good enough to be able to do this. And then from space with something like Spitzer, it's essentially hopeless for these kind of levels. So you can't, with Spitzer, detect levels that are the levels that you could not detect with Spitzer could still cause you a problem with HabEx or LUVOIR. And so what the LBTI is a nuller. It uses nulling interferometry, and essentially the way that I think of it is like a double slit experiment with a phase shift in one of the apertures. So you point it at a bright star, and so any on-axis light interferes with itself and is nulled out. So you don't see the star if the system is working perfectly. But any slightly off-axis light, which is about 100 milliarc seconds for this instrument because of the wavelength of 10 microns and the baseline of 14 meters, so this turns out, so this is 1 AU for a star at 10 parsecs, then that light will get through. And so this is how LBTI gets to much greater sensitivity than you could do with any other method. Or that you can, and because it's a better instrument than the Keck interferometer nuller, it can do better. Okay, so, and this survey with LBTI is called the HOST survey, and so Phil Hinz is the PI of that. I suppose he's still a PI even though he's moved to Santa Cruz. And so this is a plot from Steve Ertel's paper, which is the first results from 30 stars. So this is most of the results from the HOST survey. And what it's showing is measurements of the Zodi level versus the stellar luminosity for the stars in our sample. And so the dots are detections and the triangles are upper limits. And I guess you can sort of, I don't know, if you're familiar with nearby stars, these are names like Beta Leo, Beta Uma. These are all the nearest stars. So these are old nearby stars. Vega is there too, with a range of stellar luminosities. And part of the reason for that is just to build the sample, but also we want to know is there any evidence for a change in the distribution or the occurrence rate of dust as a function of the luminosity of the star. And so the important bit for the exocometry angle is these detections around sun-like stars that are at very high levels. So this Zodi level is a unit which is essentially how many times brighter than the solar system's zodiacal dust cloud at 1 AU RU. And so I've circled these three systems which are all at hundreds of Zodis. And in particular, one that we looked at in commissioning was Eta Corvi. And so this is a system for which there's an ALMA image with a little bit of extra cartoon stuff on it on the right. And so out here, this is the debris disk that we detected with ALMA. Down here is the star. And then in here is a cartoon which is showing a admittedly tentative detection of CO in the middle region between the outer belt and the inner belt that we know exists from Spitzer IRS spectroscopy. And so this has long been thought of as a system that is a potential smoking gun for exocometry delivery of bright warm dust around another star. And this is supported, at least circumstantially, by this possible detection of CO, and that if you are scattering planetesimals inwards by planets that presumably exist in the SCAP region, then at some point they will start sublimating and you'll get some CO that contributes to this. And so, of course, you need planets to do this. Now, there are a few other systems as well that have implausibly high levels, so you don't expect that arises from an asteroid belt in situ. And so these ones, the modelling effort on these is ongoing since the survey has only finished recently. But the question we want to ask really is which ones of these look like they're consistent with exocomet scenarios, or can you instead just have a scenario that is more like in the solar system with the asteroid belt, where you have the asteroid belt and then material is just coming in through Poynting-Robertson drag. But that tends to give you levels that are more down here. So these ones look like they're more of a smoking gun for exocometry delivery. So this is a watch this space. The final paper is still being written up. Like I guess the other thing that you can take away is that so we did the survey, and we're not going to say that imaging Earth-like planets around other stars is impossible. You can see that there are lots of upper limits on this plot, and basically what it looks like is that there are some systems that are exceptionally bright, and there are a lot of systems that are not. So this is good for me in that there are some interesting systems to model, and it's good for all of us that exozodiacal dust is not going to be a problem for imaging Earth-like planets. All right, so I've actually gone a bit faster than I thought. So the summary is that we have independent evidence from spectroscopy, photometry, and circumstantially from the LBTI that there are comet-like bodies around other stars. We think we see them go across in front of their stars, and we think we see the dust that they could be delivering to those regions around other stars. Now, I think this is really, for me, I've become interested in this in the last few years, and I think it's got to the point that it looks plausible, and that this is a thing that will hopefully have legs that we can do more of, so we can start asking these questions that I put up at the start and try and making exocometry science actually a science that multiple people can do and get some useful information about. And so what are we going to do next? So the problem with the Kepler mission, as I said before, is it doesn't have many young stars in it, but I expect that exocomets, at least based on beta Pic and sort of my naive expectations, that young stars are the place to look for more of these transits. And so TESS is going to be a good thing for this in two ways, right? It's going to look, I hope, eventually it's going to look at beta Pic again, and so what we should be doing is trying to organise ourselves to get spectroscopy at the same time. Whether we'll see anything or we can figure out what we've seen, if there is a transit, is a separate thing, but we'll cross that bridge when we come to it. But the other advantage of TESS is it's going to look at lots of young stars, right? Because it's essentially looking at the whole sky. And so this is going to be hard in that young stars, rotate. And so you're going to be trying to pull out a signal that may be smaller than your rotation signal, but I think the prospects may turn out to be better than for old stars, just because the transits are going to be more frequent. As I was saying before, to try and piece together this picture for beta Pic, where it looks like you have photometric transits that are a long way from the star, but spectroscopic transits that are close to the star, then I think we're actually at the point where we can develop models to try and piece that together and essentially build a picture of some kind of typical comet that is consistent with these observations, bearing in mind, of course, that we know from the solar system that they vary wildly, but at least we need to start by just assuming that there's some kind of typical comet. And then what we can hopefully do in the future, right, if we get more CO detections, then we can start looking at this and relating the material that we see in the outer belts to the disk properties, origins, the planets that cause these things to come close to their stars. Okay, I'll stop there. Thanks.
All right, thank you, Grant. Any questions for Grant? Up there.
Hi. Two questions. One is, what sort of sizes of comets have we been able to probe so far? And also, how model dependent is the orbit fitting for beta Pictoris?
So the sizes are, so the coma sizes you can measure because you get both of the you see absorption in both of the H and K lines, and from that you can figure out an optical depth, and then you can use the depth of those lines to back out the fraction of the stellar surface that you cover. That doesn't tell you, so if you want to know the nucleus size, I'm just trying to get to this. So this is the size of the coma that is covering up the star. So this is not the size of the nucleus, and so then so the sizes go up to, so some of these lines go down to zero flux. The size of the nucleus will depend on how efficient, what you would infer from it would depend on how efficient you're evaporating material from a nucleus of given size. On the orbit fitting, I have one too few parameters to constrain the orbit. So that was why when I showed these plots, there was I didn't talk about this, there was an elliptical orbit case and a parabolic orbit case. So if I assume E equals 1, then I have enough parameters to constrain the orbit. If I don't, then I don't. So then it depends on what you want to measure. So there's a degeneracy in the parameters, like the pericenter distance, pericenter angle. But as you can see from this plot, there's not a degeneracy in the distance of transit because the acceleration is what it is. If you look at, so there are some newer HARP spectra that cover a whole night, and I think you actually not only see dV/dt but dA/dt, and so then you have enough to constrain the orbit. But I doubt you're going to have enough to constrain it better than. I think it's going to be consistent with E = 1. So.
In your remarks, there seems to be a prejudice that dust in solar systems that you're observing is in the process of breaking down. In other words, dust colliding and grinding to make smaller dust, whereas everybody else in this institution is trying to figure out how to make dust collide and stick together and make bigger rocks.
Yeah.
So do you take exception to that picture, and what's your personal comment?
So when I look at a protoplanetary disk, so some people look at a debris disk and say, oh, this is secondary dust, right? So we think it's breaking down, and this is because we think the velocities are high enough that if you have an impact, you explode. But in a protoplanetary disk, there are collisions breaking things up as well. So I don't think that's a particularly distinguishing feature. I think really what we think, the picture that we have is that in a protoplanetary disk, things are growing. The relative velocities are not high enough or are low enough that you have growth. And this has presumably got something to do with the gas. Once you get to the debris disk phase, then you have nothing to damp. And we don't think that there's collisional damping because you have a pumpkin that's being destroyed by a bullet at a few k's a second. So the pumpkin carries on as fragments but in the same direction. So they're not collisions between equal sized bodies. So we don't know what it is that at some point that cranks up the eccentricities or the random velocities such that you have destructive collisions. But what we do know is that the dust that we see, if that was only dust, that would be removed by Poynting-Robertson drag on a time scale that is shorter than the stellar age, and so it must be replenished. And the way to replenish it is through destruction of larger objects. So that's the picture, and I think that's a reasonable consensus if I look at other debris disk people around. That's not just I'm not just. That's how we picture it.
Now, there's a handful of G-type stars that have infrared excess and even Ys, like core.
Yes. Well,
do you know anything about these and whether they could be cometary systems?
So they could be. Normally, what you get with Ys detections is not a lot else because if you're resorting to Ys, that means that your system wasn't observed with Spitzer. So we have detections in the mid-infrared with Spitzer, lots of them, and they have infrared spectra that show silicate features. But the levels of those are not always. So they could be cometary, but there's not they don't look like Eta Corvi in this case that you have this outer belt, which is obviously a potential reservoir. But it could be that any time you see warm dust, it's cometary. This is a hard inference to make. Basically, with the LVTI stuff, the way that I picture that we're going to do it is you're going to have a couple of scenarios, and the vanilla scenario is an outer belt which creates dust, and Poynting-Robertson drag brings that stuff in. But because the stuff is colliding as it comes in, it ends up at a relatively predictable level. And so if you see a lot more than that, then you need another process. And based on what we see in the solar system, cometary delivery is a very plausible process.
So this is just a fun question. IAU has a standard for naming comets, typically after people who find them, so I'm just curious. They kind of have to change their standards for exoplanets. I'm curious about, have there been any talks about naming comets around other stars?
Well, so I downloaded 5,000 spectra of Beta Pic the other day. Some of those are taken on the same night, but it's been observed regularly for 15 years. Every spectrum that you look at has got 4 or 5 absorption events. If you want to name them, integers would be a good option. Interstellar things that come to us, that seems fine, but presumably we'll get swamped with those. It's just like Ceres was a planet, and then Alice, and then eventually you give up. Same with Pluto.
All right. Any more questions? If not, let's thank Grant again.